All right, all right. Hello, my fellow YouTubers. Let's do a quick little experiment. First, this is my capacitor being charged by a rubber band. This thing is blowing up. Now, to think how a rubber band can do this is amazing. Well, let's go over here and look at this setup. I got a 12-volt battery. It's going over here to a 2N3055. Also a resistor. And what we're doing here is on the base of the 2N3055, you have the bottom lead of the secondary coming into the base, and then coming out of the base as well, I got a resistor, and that resistor goes into the positive leg. Now on the emitter side of the transistor, that goes to ground, and then coming off the collector, the chassis, that runs over to the inside part of the primary. Now coming off the positive, I am bringing that over here and making contact with the primary and going to light up a light bulb. So if you remember yesterday, I got some nice scorch marks, which this coil should have scorch marks. If you watched the video I made yesterday, or should I say the previous video that I posted, I'm putting through this 15,000 volt 60 milliamp, and it's 30 gauge wire, guys. The wire I've been using, say on this coil here, is I believe like a 24 or 22. This thing is clicking on its own because there's so much energy in there. Builds up quick. So anyway, thick gauge wire that I'm used to using, and I said, well, I started thinking about resistance, resistors, and just different materials that have built-in resistance in them, and nichrome wire. So I thought I was like, well, if you think about resistance, you're resisting one ladder, one side of the, between the positive and negative. They're both ladders. So you're resisting one side. So you're resisting in, you must be resisting out. So I was thinking about the top load, releasing the energy through the secondary coming back down would be resisted. And by doing that, when this thing goes off again, there is what you're doing is you're giving the top, when it radiates out for its wave, it's putting more of a blast behind it by having resistance, because if the thing is just constantly doing this up here is dumping out almost as quick as it can go in. So you want resistance built up in there, so the bottom side is like keeps pushing this energy up into the capacitor. So your capacitance, if you had a picofarad, like I know, like this right here, it's in picofarads in your capacitance. So I'm dealing with nanofarads for the primary capacitance, but for the top load, you're dealing with picofarads with this size coil. So anyway, let's go ahead and kick this on. Okay. Got a light bulb. You can see the bulb lighting up. So this coil now is working like a champ, because of the resistance that's built in this amount of wire. So that tells me when you think about Tesla stuff that it's the resistance you're going after against the primaries. Woo, that burned my finger. Bright. It's crazy. Just a little spark. I think you can see that. There it is. Little blue tip. You can look at this. Whole thing lit up. Beautiful. Beautiful power. Beautiful wireless power coming from that. Another thing let's talk about. The battery. Now, what is going on with this battery? Well, let's talk about it. Because it's oscillating in the battery. Go do this to your battery and see if it lights up. Hell no, it won't light up. Let's see. It won't do it at all. Now, just realize that that thing is burning hot. So, you would think that the resistor I have in here and the resistance in that wire, well, the resistance of that wire don't matter here, but you would think this resistor would keep it from overheating the 2N3055. Let's try another one. I think this one will heat it up, and I don't think it works anymore, but let's check it out. But you guys at home making your own stuff here, it's pretty cool. I just got the transistor and the resistor, and you just got to build a coil. That's 30 gauge. I think it's 1,520 feet. And each turn is, I believe, a foot. Let's try this again. Let's see if we have, what are we missing? Okay, we're missing that. All right. Let's try this. Fire in a hole. Yep, she's on. All right, so. And you see over here. Light bulb lighting up. Light bulb lighting up. Light bulb. Light bulb. Car battery shouldn't be doing that, guys. So let's talk about that. So what you have is a back feed. So this going to the positive is going to the breadboard's positive. The breadboard's positive has the resistor going from the positive side into the base. The base is being turned on and off because of the secondary is given a difference in potential in the transistor, which is causing a bias, which is making it turn on and off. So coming out of the primary's end goes to the chassis. So that's the output. So with that being said, when this positive side is connected to the other side of that primary, it's the primary going straight positive from the rail to the battery, and then the negative is working its way through the transistor and hitting the tail side. So that's oscillations going in the battery. Good, bad, I don't know, leave your comments. But real quick, I wonder how we can use this in other ways. Like, for instance, by jolting the battery like this, wouldn't you think it would be like desolidation, like desulfating the battery? So the battery right now would, the plates would be having the little crystals that build up on the plates would be falling off. It's a process that what you do with the batteries. And this has been a good battery. Let's go ahead and put it back on. And you can see light bulb lit. I can take this big guy here. I'm not even touching it. Light bulb lit. All right, so that's even wilder. Look, light bulb's lit, and I'm what, 6 inches away from the car battery. So the car battery here is acting the same as this over here. So the waves are coming out of this coil, and between the battery and the coil, the light bulb's staying lit. Just want you guys that are doing Tesla coils and Slayers and stuff to understand there's more going on besides just using a transistor on a coil. I mean, the resistance built in this coil, whether I go more turns or less turns, or thinner wire for more resistance, works for you or against you. Depends what you're designing. This is getting real hot. So that means I'm pulling a lot of wattage. And if I'm pulling a lot of wattage through here, I got to look and see how I can cool it down a little bit. I mean, I can use my heat sink, but it's real hot. So I know I can do something electronically to cool it down. Leave your comments out there, guys. Most likely change the resistor or add a capacitor, a little electrolytic capacitor coming off the negative side might help bring down the temperature, because if you're getting heat, you're getting a lot of volume going through there, and with the volume, you got a question is like your frequency is based on the coil. The coil is driving the frequency that's going on in the transistor. The transistor will overheat if the current is strong through the transistor. So you have to defer the heat. Now, heat sinks is a way to defer it, but also you can go after the energy inside the transistor. You're not depleting from the load, which is the primary, which is running straight off the battery, but you're depleting from the bias between the base, which is the bottom of the secondary, and the negative side of this. The negative side of the battery goes through this in order to go through there, so the heat's being built up in this casing. So you guys, hope you appreciate my vids. Leave your comments. Let's see how much energy we got built up. My dog's running. He knows this thing sounds like lightning. Woo! Been hit by that thing, but not that strong. And I'll tell you, this thing sent me on the floor. It's crazy. And all it is rubber bands, which gives me an idea of taking a tube and blowing air through it.